So yeah, this is some research that I did at Brown related to um, looking at the radiation effects of the silicon sensors that they use to detect, um, different charged particles from the collisions at these different sites. So I'll talk about what is the LHC, what is CERN about silicon detectors, talking about radiation damage, and then the experimental setups that we use in order to determine exactly how much radiation damage occurred on these silicon sensors, and some general conclusions. All right, so first, the Large Hadron Collider in CERN. So at the LHC, there are four main experimental setups: CMS, LHCb, Atlas, and Alice. So I was primarily working with the CMS collaboration. You can see, actually, let me annotate. You can see this big spiral arm here. So that's actually where all the proton packets are getting accelerated to something like 99.999% the speed of light. And then they collide at these different center locations. And what we do is we try to determine the actual offshoots from these collisions. But the issue that we're having, or the issue that can arise, is with these increased collisions, you end up having a lot more radiation damage, right? So not only are you getting offshoots that are kind of lights, like quarks that are passing through, which we can't detect, at least not on the silicon detectors, but you're getting these very heavy, like neutrons, protons, that are colliding with the actual silicon lattice of these sensors that are used to detect, the paths of these particles, and then try to reconstruct exactly what was happening at the center of the collision. So with this high luminosity LHC upgrade, they're increasing the number of these collisions by 5 to 7 times. And so this question arises: how is that going to affect the performance of these different silicon detectors? Okay, so on the top plot, we can see CMS, so CMS, compact neon solenoid. At the very center, you see these silicon trackers. So silicon trackers here, and it's basically this region here. And this thing is absolutely massive. So here's a person, this thing is maybe like 30 meters in diameter, maybe like 60 or 70 meters in length, absolutely gigantic. And what's happening is the protons are coming from this direction, the protons are coming from this direction, and then they're going to collide right in the center. And these silicon detectors are going to be the first things that the byproducts from these collisions see. And from that, they're going to be able to determine the path of the different particles. By the way, throw questions in the chat if you have any questions. Oh yeah, very cool, very cool. It's a beautiful place. All right, so this is the center barrel where you can see the different silicon detectors. So each one of these little rectangles is one of those silicon detectors. The lab that I was working on is responsible for building, I think, like 40% of all the silicon detectors that are going to go at CMS. And then part of that mission is to try to determine this radiation damage effect. So the byproduct of the collisions hit the silicon sensors before any of the detector elements, and they effectively work as electronic ionization chambers. So if you guys have ever seen any photos or videos of these ionization chambers, what they do is they put a gas in there, and like some kind of I think they usually use like alcohol. They turn that into a gas, and then you can actually see when charged particles are traveling through that gas, because what happens is it basically collapses that gas into a liquid, short and quick enough so that you can actually see these little tracks. So that's what we're trying to do with the silicon detectors. Each one of these little pieces will activate if a charged particle goes through, and if you have enough of these different silicon detectors, you can kind of reconstruct the path that the particle took after colliding at the center of this particle detector. Okay, so silicon, very pure silicon has a crystal lattice. You can dope it with either a extra, so you dope it by adding a element which has either one additional electron, so that electron will be doing the completing the circuit, or you take one electron away, and then you have like this thing that's called a hole, and that hole is going to be basically what's traveling and trying to connect the different parts of this this diode. And on the bottom right, you see an example of where you have these two different types of doping, N-dope and P-dope, together. And what forms is a depletion region. And there's some mathematics associated with the width of that depletion region dependent upon the concentration of the holes or the concentration of the extra charges. That's another story for another day. Okay. And then, in order to electrically characterize these different silicon diodes, we do something called an IV or a CV measurement. So IV just means that we're measuring the current after applying some bias voltage to these different silicon diodes. CV is the same thing, except for measuring something called the capacitance. And then there's some mathematics associated with radiation damage. I won't get too into this. More mathematics associated with radiation damage. More mathematics associated with radiation damage. This one I will describe. So what's happening, as you can kind of imagine, is you have this crystal lattice and you're shooting these very heavy objects at this lattice. And as you shoot them really, as they're going really fast, you're actually going to knock off these silicon atoms from the lattice, and they're going to kind of go and they're going to find another place to live, basically. And as that happens, the electronic characteristics, the electronic characteristics of that lattice start to degrade. And that is what is basically being calculated here. So we can see that on the bottom, we have fluence, basically a measurement of how much radiation the silicon has seen. And on the vertical axis, we see the change in the voltage divided by the volume of the diode. And so it's having some effects on this diode. And what ends up happening is it's not able to properly see the different charged particles that are passing through these diodes, which is obviously an issue because if you're trying to build a detector, you need to be able to detect what it is you want to be detecting. And so there's some ways of going around this, trying to improve the situation. And this is basically what's seen here. And I'll just kind of give you an overview of what this is. What's happening here is you can actually heat up the silicon lattice. And what happens is you start to jiggle the silicon lattice, and all the silicon atoms, which are not in their correct space, are going to kind of pop back into place. And this is a representation of that phenomenon. You can see that there's a minimum in this curve here. And that minimum corresponds to the ideal amount of heating, not only the temperature at which you're heating, but also the duration of that temperature, where it kind of gets your silicon atoms back into their best and optimal state. You can see that this curve starts to go back up. This is basically an indication that it's going to reverse. So it's actually going to end up getting worse at a certain point. And so being able to predict exactly where that's happening is really, really important. And there's some things you can do in order to predict where that might happen. Okay, so these are the actual diodes that we were working with. So on the left-hand side, we see a few different shapes. So this one is a little bit bigger than that one. The actual active area of these diodes is basically this gray region here. And then these little spots here are actually guard rings. So what they do is they limit the extent of the active area of the diode and kind of keep just the active area, the charged area of the diode just constrained inside of that region. When you guys, or if you guys are in an AP physics class, you guys might have learned about parallel plate capacitors. And in learning about parallel plate capacitors, you probably learned about the fact that your field region inside of that parallel plate capacitor actually extends out into space. And what these guard rings are doing is trying to limit that region by basically applying a ground voltage on the extent here and basically limiting those fringe fields. Does it mean that you can heal it, or does it degrade slower? You can heal it, yeah. So that's like heating up is kind of like a healing. So you're kind of wiggling this, like temperature, as you heat things up, what's really happening is things are just kind of shaking a little bit. And as you're heating it up, as you shake this silicon lattice, those silicon atoms which popped out of place are able to pop back into place. But then as you heat it up further and further and further, you get up into the other issue where you actually start to break down this silicon lattice in some way that I won't go into here. But that's what's being represented in this plot, where that minimum is the optimal amount of heating to get your diode healed. Okay, so this is the setup that we used. So what's here is basically these images here, these diodes are resting on a plate over here. And then we're applying some voltage using this box. We're basically calculating capacitance using that box. There's a bunch of other instruments using, trying to control the temperature of the environment, et cetera, et cetera, et cetera. Okay, and then there's another setup, which is pretty interesting, that we were using. So not only do we want to electrically characterize these diodes to infer, where they are on this healing process, but we also want to try to mimic what's happening inside of CERN. So what we do is we can actually place a little radioactive source here, and that's going to shoot electrons at our silicon sensors, and we're actually going to be able to pick up those signals from those electrons hitting our strips. Those sensors, those readouts are going to be sent to this little chip here, eventually through this ribbon cable, and then eventually to a computer. That computer picks up those signals here, and we can actually see where the strontium source is, which is emitting these electrons. Electrons are basically just 200 times less the weight or the mass of muons, which is what these silicon sensors are intended to capture. So from here, we can kind of reproduce what is happening at the compact muon solenoid. This over here is where we're trying to wire bond those little strips. The strips are, you can't even see, they're actually thinner than the width of your hair. So even if you were like looking right at it, it would just look like flat material. You can actually distinguish the different lines. And then here, these cords are used for some little diodes that are on the edge there. And yeah. Okay, so we're decent on time. Yeah, so this station again is trying to recreate what's happening at the compact muon solenoid. These have been irradiated at a location close to Brown called the Rhode Island nuclear something. And there they're bombarded with neutrons. So they're not exactly seeing the same kind of radiation profile that they would see at the compact muon solenoid, but there's a way of converting between these different radioactive this different radioactive damage. And so what we can do is we can try to heat this up, do that healing, and try to find where the optimal amount of heating gets us to the best performance after radiation. So this is what that station does. Okay, and this is actually how we irradiate those sensors. So this whole canister is filled with dry ice. As you can imagine, a nuclear reactor is very hot. So we use dry ice in order to maintain the temperature as cold as possible for as long as possible. One of the issues that you run into is as you're radiating these silicon detectors, and if you're concurrently heating, right? So you have this effect of like, okay, you're damaging it, but then you're also healing it at the same time. It's not exactly a linear trade-off. So you want to try to reduce all the possible, you want to just focus on one of these things, right? You just want to focus on, hey, I'm just going to irradiate to this amount. I don't want to worry about all these other things that can happen. So this is one way that we help reduce those other things that can happen. We take the temperature during it. Here's some larger sensors, actual sensors that could be sent to CMS to do some particle path reconstruction. Yeah. Cool. Okay, and then this is like some analysis of these sensors and seeing where that minimum spot is. So if you remember the plot that I showed you before, it kind of looked like this, and then kind of went up. This minimum point is where the optimal amount of heating is to get it to be more or less healed. You can see that occurs basically there, it occurs basically here, here, and here. And the difference between these two different runs is these were at the back of that tube that I showed you. These were at the fronts, back and fronts, and they had different temperature profiles. So here's a plot of the temperature. This yellow, it's barely visible, but these are the fronts. So the front are experiencing the brunt of the heating inside of the nuclear reactor. These blue ones are experiencing much less heating. And so you see that it takes a lot more, and then also the fronts are experiencing a lot more radiation. So it takes more heating in order to get that to be more healed as compared to the one at the back, or rather, sorry, the front one experienced so much more heating that it doesn't take as much heating to bring it back to that healthy spot as compared to the one at the back, which didn't experience as much heating during irradiation. The same story is over here, except they're more overlapped, so the minimum occurs more or less in the same spot. Some values associated with those fits for that. Alrighty. And so basically, the conclusion of all that analysis netted out in finding that it wasn't a linear trade-off between the heating in the reactor and finding where that minimum is. It was more of a log relationship. So we see on the log the cumulative annealing on the y-axis. We see this minimum value on the x-axis. And so it's not exactly this linear trade-off. And this is going to help us to anneal these silicon sensors in a more informed way, instead of just throwing them in there and expecting that they're going to be irradiated with the same amount, despite the fact that they're seeing different annealing temperatures during radiation.